Okay, so welcome back. Today we'll talk a lot about modeling with integer variables, modeling with nonlinear variables, and I'll start with modeling nonlinear problems. And then tomorrow we actually have a case study, a couple of case studies, one on the design of a thermal insulation layer for the Large Hadron Collider, and another one on the power grid. Basic nonlinear modeling tips. And we're going to do something to the lights here in a moment to make it easier to see. Okay, so for now, for this lecture, we're going to ignore the binary variables, and we're just going to look at problems that are nonlinear optimization problems just over continuous variables. So here we have a nonlinear optimization problem. It's got an objective function that tells us the goal of what we're trying to optimize. It has a set of constraints, nonlinear constraints, and typically we can have much more general nonlinear constraints, but we allow both lower and upper bounds. So you don't need to write your problem in this specific format, g of x less than or equal to 0. And we also assume there's some simple bounds, and there's the set x, which is the set of simpler constraints. So in this case, for example, polyhedral constraints, linear constraints. And you want to often separate those out because the solver can take advantage of these constraints. So for starters, when you form gradients, or when the modeling package forms gradients, and you can have other classes of constraints. So if you're interested, you can have differential algebraic equations. So that's a system of equations where you have control variables that are discretized over or that live on a time horizon, and ordinary differential equations, or you can even generalize this to partial differential equations. But we're not going to talk about these in this course. Okay, so here's the first small modeling trick, and this is something that arises, for example, in inverse problems. When you prepare weather forecasts, there's a problem called 4D VAR, which stands for, which is the problem where you assimilate data into your weather model. And in these problems, what you often see is there's often a low rank Hessian matrix. So here we have at the top, there's a quadratic function, q of x, that could, for example, be your objective function. And the Hessian matrix W has the special structure where W is made up of this product of Z transposed R inverse Z. And don't worry about R inverse for a moment. That's typically a non-singular covariance matrix. That's why the inverse is there. You work directly with this matrix. You typically don't work with inverse matrices. But Z, the matrix, or Z, the matrix Z, has many fewer rows than columns. So that means that this product up there, this W, if I write it out, W can be is a square, a big square matrix, and it's made up of Z transposed. So Z transposed is a long and skinny matrix. Then you have a little matrix, R inverse, and a short and fat matrix, Z. And so this is a low rank matrix, and the rank of this matrix is at most m, the number of rows in Z. And if you do that, there's a very simple trick. You can introduce an additional variable. So you just introduce this new variable called Z, which is just the product of Z times X. And if you do that, then your objective function, or the quadratic term X transpose WX, just becomes Z transposed R inverse Z. You can just check that. On the right-hand side here, the Z becomes a Z times X. So that's okay if you compare the red W there and then the Z transposed. And you can often exploit sparsity. For example, if there's sparsity in Z, then this additional equation can be solved efficiently. So this is sort of a simple modeling trick that sometimes arises. And I've seen it mostly in inverse problems. And it turns out that if you do this, you can solve this problem much faster. Also because W can often be a dense matrix, whereas this product is much more efficient, and you can store it much more efficiently as well. So this is quite important. The second modeling trick is, we were talking yesterday that it's better to have convex or linear constraints, and so here's a little trick that shows you how to get from a non-convex expression to a convex one. So we start off with this bilinear term x1 times x2, and I'm going to assume that my second variable here, x2, is a binary variable. So then, if x2 is a binary variable, then this bilinear term x1, x2 can just have two things that come out. It's either 0. If x2 is 0, then the product of x1 and x2 is 0. And if x2 is 1, then you get x1 coming out. So there's only two values that come out, or two ranges of values that come out. You can model this by introducing a new variable. I call this x12 to indicate that it sort of concerns this product of x1 times x2. And then you introduce these constraints. And the constraints at first sight might look a bit much, but it's actually easy to see that they encode exactly what you need to do. And to see that, what I do typically is I just substitute the two cases. So if x2 is equal to 0, then this first equation here gives me that x12 is equal to 0. I get that. And then over here I have some upper bound that I have. So this negative upper bound, x2 is 0, that lies between the difference between x1 and x12. So, so whatever x1 is, it will satisfy this constraint, which is just minus u less than or equal to x1 minus x12 less than or equal to u. And then the second case, there's only two cases, x2 is equal to 1. Then this first constraint is sort of the inactive constraints or the floppy constraint. So it just says x12 is less than or equal to u. And the second constraint now, if x2 is equal to 1, then I get a 0 is less than or equal to x1 minus x12 is less than or equal to 0 on the right-hand side. And so I get out of that that x12 is equal to x1. And that's it. And so a very simple modeling trick, but very effective. And we use this a lot. Those kind of constraints where you have an upper bound constraint on x1, they're also called variable upper bound constraints. And the solvers sometimes can exploit those directly. Here's a more complex or more involved variable transformation. This comes from a multi-product batch plant design. This is one of Ignacio Grossman's problems that he looked at. So I talked to you about that he's sort of the grandfather of mixed integer nonlinear programming. And if you look at these, the first expression up there, you have an objective function. It's not the complete model. It's just two of the constraints in the objective function. And this looks really wild. So the variables here are n, the nj, vj, ci, nj, and bi and ci. Those are my variables here. So everything that's colored are variables. And this is certainly a nonlinear, non-convex optimization problem. But in this case, it turns out you can transform the variables. So instead of looking at the variable vj, you look at the little vj, which is the logarithm of vj. And similar for n, b, and c. So you transform all your variables using this logarithmic transformation. And then you need to remember your high school math, which is not always easy. And it then turns out that, okay, so the first term is nj times vj to the beta. So you can sort of work this out that e to the little nj plus, what's the one, bj, or beta j times vj. That's the same as e to the natural logarithm of capital Nj plus the natural logarithm of beta j, of vj times beta j. And so that just turns out to be nj. Then you have to remember that the plus becomes a multiplication and the beta j becomes an exponent. So that's exactly the expression that you had there before. How you come up with these transformations, I don't know. So people like Ignacio, they write smart papers, but they don't tell you how they came up with these smart reformulations. But there are a lot of these around, for example, for multi-product batch plants, but also for cutting stock problems. There's other reformulations. And the nice thing about this reformulation is that these expressions down here are now convex. So we started off with a non-convex problem. We did this variable transformation. We have new variables, and the new problem is convex. So here, for example, this is just a linear constraint with a right-hand side that you can evaluate, and exponential functions are convex. Right? And so you have a nice convex optimization problem, and we can solve convex problems much more efficiently than general nonlinear ones. Now, the next little pieces that I have are from a book that I found recently. Let me just go forward. Yeah, this is Adam Levy's book, and it's a really nice book, An Introduction to Optimization, that came out, I think, in 22 or so. And he has these simple rules, which I love. So one is keep it simple. So when you're modeling, there's a tendency to model what's in the physical world. So you could say, well, I have a ratio of two quantities, and I want to keep this ratio between certain bounds. And that's okay, but you can reformulate that expression on the left there equivalently, provided that the denominator is non-zero. So take this equivalent sign with that one caveat. You can reformulate it equivalently by simply multiplying through by 4x3 minus 2x4 and pushing that on the right-hand side. And so now what I did was I had a nonlinear expression, it became a linear expression. In fact, I had a non-convex expression, and now I have a convex expression. Another really important aspect is to keep it lean. So we want to have small coefficients. And again, when you're modeling things, there might be a tendency to work, I don't know, in Italian lira versus German Deutschmark, but 1,000 lira are 1 Deutschmark, and so you could also reformulate your problem and have smaller units that you're working with. A very important part of optimization is also that you want to avoid having coefficients which are very unbalanced. I've seen models where you have coefficients that are of the order of 10 to the minus 6, and then coefficients that are of the order 1. And so those are very bad constraints because they introduce numerical issues when you do matrix factorizations. So again, we prefer linear or affine constraints. They ensure convexity, and this is a really nice reference. It's a nice little introduction to optimization. Did I just go? Yeah. Another thing to do is you want to help your solver. So nonlinear optimization solvers are very well developed. There's a lot of theory has gone into it, but it's a much harder problem than linear optimization problems. And so as a consequence, they're a little bit more fragile. So, but you can help your solver by, for example, if you have linear expressions, to keep them separate. And here's a sort of simple rule that applies to almost all nonlinear optimization solvers. So I can guarantee constraint satisfaction up to certain tolerances, depending on what kind of constraints I look at. For example, if I have simple bounds, then one of the solvers that I wrote guarantees that if xk is greater or equal to 0, any subsequent xk will be greater or equal to 0 on your computer. So it's not up to precision. This is exact, and you can do that by just truncating very small values. It's okay to do that. Linear constraints, they hold accurately. So the solvers will guarantee that if a linear constraint is satisfied initially or in the end, then the residual between the sort of left-hand side, A transpose X, and B is less than or equal to kappa, where kappa is a small constant. And for most solvers, for active set solvers, this kappa will be about 10 to the minus 12. So it's non-zero often. You can't make it zero. Typically, it's something like it depends on the condition number of your matrix A, and it's a constant times that condition number. So most solvers will ensure that these constraints will hold very accurately. But nonlinear constraints, they only hold in the limit. And so this is sort of where k goes to infinity. And of course, we never go to infinity. You don't want to wait that long for your solver to finish. So typically, the termination condition for for nonlinear constraints is something like 10 to the minus 6. So we have three types of constraints here. Simple bounds, you will get it exact greater or equal to 0, or if it's less than or equal to 1, exactly less than or equal to 1. There is no round-off error in these constraints. You can ensure there's no round-off error. For linear constraints, you have errors that are proportional to the unit round-off error on or machine precision on your laptop. So 10 to the minus 12, something like that. And for nonlinear constraints, you just have an epsilon that's 10 to the minus 6. So 0, 10 to the minus 12, 10 to the minus 6. That's the accuracy you can sort of expect, roughly. A lot of that also depends on conditioning. So here's a mini exercise, and you could do this now. And I think we should do this now. So grab a piece of paper. This is really cool. So you have a constraint that says the logarithm of x2 cubed plus 1 plus 2x1 is less than or equal to 0. There are no other constraints in your problem. So there's no bounds on x1 or x2. You know that you can't evaluate logarithms for negative numbers. So how do we make sure that we stay safe? Which constraints should we add to ensure that we stay safe, that we never evaluate a negative logarithm? So I'll give you, I don't know, a couple of minutes. So do it right now, and then I'll go over the solution with you guys. And there are three answers. Okay, does anybody know why there are three answers? Only one is correct, but why are there three answers? Quick guess, anybody? X2 should be greater or equal to what? Oh, okay. That should work, yes. There are three ways of doing it, and you got the best way already. There's three ways because you can effectively use those three techniques that we have there. So here's the bad one, the one that you don't want to do. So there's a bad formulation, which is to simply say, oh, I take whatever is inside my logarithm, and I just add a constraint that says x2 cubed plus 1 greater or equal to 0. But I just told you that the solver will not guarantee that this holds. This will only hold in the limit. So it might still evaluate this for negative numbers. So that's not a good idea. Now you had a better idea. Actually, yours is better than mine. So what I do is a sort of general idea, which is I introduce a slack variable. S, and then I set S equal to x2 cubed plus 1, and I have S non-negative. But you're right, if I just ensure that x2 is greater or equal to minus 1, then that's a much, much better solution. So I like your solution better. So this is the good solution. This is okay. The one that I have here is sort of a general form. If you somehow can't solve this expression, right? If I had made it more complex, if I had more variables in here, then I might have easily come up with a linear or simple bounds there. So if I did, instead of this, if I did the logarithm of x2 cubed minus x1 plus 1, then it's harder to see what you need to do right now. So introducing a slack variable, putting the slack variable into the logarithm, and then just safeguarding it. That's it. There's one additional thing you need to do, and you're not yet safe. We're going to talk about modeling languages later on. And modeling languages, when you write these constraints down, they have an initial guess that they assign to variables. And the default for the initial guess is what? What do you think is the default for an initial variable guess? 0. Of course it's 0. Why would it be anything else? So that means if I just wrote this down like this, my initial guess for this nonlinear solver would be 0, and it would already stop at iteration 0 and tell me that I'm trying to evaluate a logarithm at 0. But I can change that and simply have an initial guess that's positive here. Anything will work. Okay, here's a very important slide. Never replace a binary variable by a nonlinear expression. And people have written papers about this. So there's literature on this. And every 20 years or so, somebody comes up with this very same idea. So I can look at this binary variable y, which is 0, 1, and I can replace this equivalently by saying y is between 0 and 1, a continuous variable. And if I multiply y by 1 minus y, it has to be 0. So this looks like there's y. Here is y times 1 minus y. There's 0. There's 1. That's what it looks like. And this function is 0 at exactly 2 points, right? You can actually relax this. You can also say y times 1 minus y less than or equal to 0, which means this nonlinear function has to be less than or equal to 0, so it has to lie below the half plane here. But because y is between 0 and 1, there are just these 2 points. Another way of writing this is as a complementarity constraint. So complementarity here means that either the left is satisfied as equality or the right is satisfied as equality. But they can't both be, either the left is positive or the right has a positive residual, but they can't both be positive residuals. And again, that's, if you reformulate this, some nonlinear solvers reformulate this complementarity constraint by just multiplying the left by the right, and you end up with that same expression. So there's papers in the literature that tell you to solve problems like this. And in topology optimization, that's actually what some of the algorithms do there is they assign material to different finite elements in your domain, and then they sum over all the finite elements, and they have a term like this that they're trying to drive to 0, penalty term in the objective function. But we don't want to do that because there's structure in the binary variables that we'll exploit in the algorithms that we'll tell you about tomorrow. Now, here's another bad nonlinear model. You want to switch on and off a nonlinear constraint. So here I have a nonlinear constraint g of x, but I want this constraint only to be enforced if y is equal to 1. So if you remember the flow sheet that I had in my first slide, that was there's a condition there that says basically if I choose to do a certain process, then for that process I have a set of nonlinear constraints. And if I don't have that process, then I can ignore this. So a very tempting way to do this is to simply multiply y times g of x. And you can quickly check that exactly implements this constraint. If y is equal to 1, you have g of x less than or equal to 0. If y is equal to 0, then you don't care what g of x is because 0 times anything finite will be less than or equal to 0 or equal to 0. So you're okay. But we don't like doing that. There's really two reasons. One, it potentially introduces non-convexity. And two, and that's less well known, somebody mentioned constraint qualifications yesterday. This actually violates Mangasari and Fromovit's constraint qualification. So whoever mentioned constraint qualifications yesterday, I can't remember who you were, but you should be happy now that there's at least, we can talk about that here. Instead, what you should do is you find an upper bound on your function by maximizing over the range of variables that you can put there. And this could be also constrained by other constraints in your nonlinear optimization problem. And then you write this upper bound constraint here. And so now if y is equal to 1, that will be 0. So g of x is enforced. If y is 0, then g of x is below the upper bound, and that's a valid upper bound on g of x. So that means you inactivated this constraint. So this is a much cleaner formulation. Why do I want to do this? Oh, because yesterday I had an example. We had a product stream that we could split into two streams. And there were two process boxes here. So we had a process 3, and here we had a process 2. There was another input that came out, and here was another process. And we had binary variables, y2 and y3, that told us which of these processes is active. And so if y2 is 0, then I'm not using this process. I don't want to constrain my variables by whatever is in here. Let me see if I can think of another example really quick. Does anybody know a good example here? Right. So this is valid. Yeah. Was that your question? Okay. So g of x is always less than or equal to u because you found the largest value for g of x. So this is always, if y is 1, then the right hand side is 0. If y is 0, it's gone. And the reason is that we are switching constraints on and off depending on what we're doing. In aircrew scheduling, for example, you decide what size plane you're flying from Mumbai to Delhi. Once you decide you're going to fly a 787, you need more crew. So you have a constraint that says I need, I don't know, 15 people, 15 crew. If you're only flying a 737 MAX 9, which I hope you don't, because they seem to be falling out of the sky. If you're flying those, you need fewer people, right? And so the constraint is different. So you don't want to enforce the 737 constraint on a 787 because it's a different aircraft. So you make the decision which aircraft do you fly, and then depending on which decision you make, you either have one set of constraints or a different set of constraints. And that's also called disjunctive programming sometimes. Okay, good question. Okay, I haven't really given you much time to ask questions. Nonlinear constraints are a really powerful modeling paradigm. We can model a lot of things with nonlinear constraints. In particular, we could model binary variables with nonlinear constraints, but we don't want to do it. And so I like this quote that with great power comes great responsibility. So please use your nonlinear constraints responsibly. And then we're re-emphasizing this. Linear constraints are easier to solve, easier to manage than nonlinear constraints. There's sometimes useful nonlinear transformations for convexity. And there exists a number of those in the literature. You can often simplify by linear terms. And the one thing we should not do is multiply a constraint, a nonlinear constraint, by a bilinear function. There's other ways of handling those constraints, and they're more efficient. Okay, so let me see if there's any more questions. It doesn't look like it. We're going to be Yes.
So you mentioned a way to represent binary variable as a quadratic term.
Yes.
So for a solver, would it be better if we just specify that it's a binary variable?
Yes. 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 Please. Please do that. Never do this. This is red warning. You should not do this because you lose structure. The nonlinear solver will not realize that if you give him these constraints, it's very hard for the nonlinear solver to realize what you really mean is that y is a binary variable. And our solution techniques are much better for binary variables. We have a much better handle on that. Sorry? Yes, both are bad. Yes, good point. Yes, please read all the slides, and I should read all the slides. So here's what a nonlinear solver would do. If you gave this to Pietro's solver, let's see if I can get this right. He can correct me if I'm wrong. One way of handling this constraint would be, for example, this is not necessarily what Pietro does, but one way to handle it might be to replace it by a piecewise linear function. That's one way of handling it. Another way of handling it would be to find supporting hyperplanes and build the convex hull. So I can also find two functions and maybe even a third. And now I replace this constraint by the condition that I have to lie inside this set. So this is now convex relaxation of this quadratic constraint. And so these are just tangent planes that I've drawn here, so I can do this potentially. But now I've changed the problem. Before, I had two feasible points. I had this point here and this point here that were feasible. Now I have this whole region that is feasible. And so that means when I solve this relaxation, I will end up at a point somewhere out here, and then I have to do some mechanism for getting rid of this point, some branching and bounding, and it's horrible. So we don't want to do that. In principle, the solvers could detect that because that's structure that you could look for, but I don't think they're doing that at the moment. So yeah, don't do what's on this slide. Never do what's on this slide. If there's red things, red is warning. Don't do the red things, I hope. Any more questions? If not, then we'll take a short 15-minute break or so. We're back here just before 10 o'clock. Thanks.